Now we're going to try to put some of this stuff to use to a problem. We're going to try to find the maximum velocity, the average maximum velocity for water flow in a pipe that has a diameter of 3 centimeters. We get a surface roughness of 0.05 millimeters, and m dot is equal to 0.8 kilograms per second. So the first question you should be asking is, is this actually going to be turbulent or laminar? And so, we'd like to get a Reynolds number. We could figure that out. Obviously, that's going to really determine which relationship we use. We know there are two different relationships we could be using, and we need to know which one to use. One for laminar, one for turbulent. Because we have an epsilon, you could think, oh, it must be turbulent. But, of course, I could just be tricking you. And, of course, if you were out really in the engineering world, you would have this information no matter what. I mean, that's something you could look up for your pipe. And whether it was important or not would depend on whether it's laminar or turbulent. So let's go ahead and figure out if we can get a Reynolds number here. So for the Reynolds number based on D, I need U, D over nu. I know nu. Nu is 1 times 10 to the minus 6 meters squared per second for water. That's easy. D I've been given, it's 0.0, D equals 0.03 meters. So that's simple, but I need U. And so I got to get U from this m dot. You guys have been doing this a lot recently. Hopefully you're good at it by now. M dot equals rho A and then times the average velocity, right? So that's my average velocity there. That will give me a mass flow rate in any situation if I have a pipe or any kind of duct that has an area A, cross-sectional area. So I can solve that for my average velocity. I have m dot, which is what I was given, and rho and A. So easy there. And so I just plug in my values. I need my A. So first, I guess I'll calculate that. A is equal to pi d squared over 4, which is equal to, in this case, 7.07 times 10 to the minus 4th. So there's my area in meters squared. And now I can go ahead and plug in all my values. So I've got 0.8 kilograms per second. I've got 1,000 kilograms per meter cubed for the density of water, and I've got the A, 7.07 times 10 to the minus 4th meters squared. Some of you are still getting these flow rate kind of things confused. You're putting in kilograms when you're, and putting in different units to get different things that don't make sense. Notice this all should work. I mean, this is supposed to be a velocity. It should be meters per second. Kilograms are going to cancel. I'm going to get meters here. So it's going to be 1 over meters, and that's going to be perfect. That's going to pop up and give me meters per second. So the units really should work and should tell you if you're using the right formula. Velocity is meters per second. So you can certainly do a unit check on that. Make sure you're using the right things here. All right, anyway, in this case, you plug all those numbers in, you punch it into your calculator, get 1.13, and it's meters per second. So there's my velocity. Now I can easily calculate my Reynolds number. My Reynolds number based on D is going to equal 1.13 meters per second times 0.03, which is my diameter, divided by that 1 times 10 to the minus 6 meters squared per second. And that gives me a Reynolds number of 33,900, which is very, very turbulent. So for pipe flow, we know that a Reynolds number of 2,000 would give us turbulence to be the transition point. We're way, way, way beyond that. This should start to give you a sense for, like, when you have real water flowing through a pipe, you're probably going to have turbulent flow unless something's really, really small. So if you have really tiny pipes, really unusually small pipes, or you have really, really slow flow rates, you could get something that's non-turbulent. But in truth, most water in a pipe flow is going to be turbulent if you're talking about sort of the usual engineering scales at which we work. Of course, there are microfluidics and things that people are working on now, very cool fields where you'll see very small Reynolds numbers, but a lot of times these flows are turbulent. Probably your assumption should be, if you're looking at water flow in a pipe, it's probably going to be turbulent. All right, so anyway, back to my problem here. I'm trying to find the U max based on this U bar. So I now know U bar. I just calculated that. It was 1.13 meters per second squared. Now I want to try to find this guy, this U max, time average maximum velocity, but I have a formula for that. So it's n plus 1 and 2n plus 1 here. So that was the formula we just derived. And it's pretty easy, except I have my U max. I know my U bar here. So I have I have one unknown, one equation if I knew n, but I need n. So I need n here. And n, we know how to find n too. N is equal to 1 over the friction factor, square root of the friction factor. All right, so there's that. So I need F. So I need F. Well, I know how to find F. F is going to be the Moody diagram. And in order to use the Moody diagram, I need two things. I need the Reynolds number, which I already have, and I need epsilon over diameter, which is the roughness factor. And so in this case, the roughness factor is I have 0.05 millimeters over the diameter, which is 3 centimeters. So I could rewrite that as 0.005 centimeters over 3 centimeters. Of course, I could also just convert it to meters. Doesn't make any difference. It's dimensionless at the end of the day, as long as I have the same dimensions in both places. Here I've got centimeters and centimeters. That is fine, but pay attention and make sure you have the same units in the top and in the bottom, and therefore your answer will have no units at all. So epsilon delta over delta is equal to 1.67 times 10 to the minus 3. All right, and my Reynolds number, I already found that. It was equal to 33,900. So now I'm ready to go to the Moody diagram and pull off an F. So I'm going to go ahead and grab my Moody chart. Got it very handily right here. I think you can kind of see it. It's a little bit hard. I'll zoom in a little bit here. Okay, so here we are. And what would I say my numbers were? They're 1.67 times 10 to the 3. So that's like almost 2 times 10 to the minus 3. So that's going to be this line here. 2 times 10 to the minus 3. And then I'm going out to a Reynolds number of 34,000. Excuse me. 34,000. Well, this is 10,000. So this is going to be 35,000 is here. And coming over there is that guy. I'm trying not to write on this chart with pen. And I get like 0.2, 0.028. Yeah, 0.028-ish about. So F is about 0.028. So I'll zoom back out. About, I always put an about sign there. This is, you know, as I said, you're reading the Moody diagram. You're not pretending to go out to, you know, lots of sig figs here. You're lucky if you can get 2. So I got 0.028 as my friction factor, roughly. So that allows me to calculate my n. So I put in my n is 1 over the square root, 0.028. And that comes out to be approximately 5.98. So, well, that comes out to be exactly 5.98. It's this thing that's approximate, the 0.028. But so my n is 5.98. That means that U max, with a little tilde sign, is equal to the average times 6.98 times 12.96 divided by 2 times 5.98 squared. Right? So where's all that coming from? That's all coming from up here. I just put in 5.98 plus 1, 2 times 5.8 plus 1, it's 12.96. I've got the 2, and I've got the n squared, so that's all solving for U max in terms of U. So that gives me that the U max is equal to 1.26 times U bar, which is 1.13 meters per second. And that gives me my answer, which is that the U max, the time average maximum velocity for this problem, is 1.42 meters per second.